Hello, in this lecture, we are going to start with the things that we were doing in the previous lecture, that is linear transformations. One of the important concepts regarding linear transformation is the matrix representation of linear transformation that we did in the last lecture itself. Although I found that not many people followed it, so therefore I am revisiting the same concept. Okay, so let U be a so I have defined let U be a linear transformation, that is let U be an n-dimensional vector space, and let's say this vector space and V be a n-dimensional vector space n. Okay. Now, if T is a linear transformation from U to V, okay. So if U is a U is a m-dimensional vector space and V is an n-dimensional vector space. Okay. And if we want to just give me. So let T be a linear transformation from U to V. And let us say the basis of U is alpha 1, alpha 2, dash, dash, alpha m. And the basis in V is beta 1, beta 2, dash, 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 beta n. Now, alpha 1, alpha 2, alpha 3, dash, 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 alpha m are the bases in U. So clearly, I can say that T alpha 1, T alpha 2, dash, 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 T alpha m would be contained in V. And since they're contained in V, I can write T alpha 1, T alpha 2, all these things. I hope it is visible now. Okay. So if T alpha 1, T alpha 2, dash, 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 T alpha m are contained in V, then I can write T alpha 1 in terms of the basis set in V. So the basis set of V is what? Basis set of B dash, basis set of V is what? It is B dash, and B dash contains B1, B2, B3, dash, 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 Bn. So I'll write it as A11, beta 1, A12, beta 2, dash, dash, A1n, beta n. And similarly, T alpha 2, I'm going to write it as this thing, A21, beta 1, plus A22, beta 2, dash, dash, A2n, beta n. And similarly, at the end, I will have T alpha m. I can write it as AM1, okay. This is how I can relate T alpha 1, T alpha 2, T alpha m with the basis of V. Please to understand, again, I'm explaining alpha 1, alpha 2, alpha 3, alpha m. They are what? They are bases in U. Now, if I take a linear transformation T, the image set, this T alpha 1, T alpha 2, and dash dash T alpha m would be contained in what? It would be contained in V. Since it is contained in V, I can say that they can be expressed as linear combination of the basis of V. And what is the basis of V? The basis of V is beta 1, beta 2, beta 3, dash dash, beta n. I hope it is clear. Now, having said that, if I want to write this in matrix representation form, so what I have to do, I'll take the, see, what I'll do, see, T alpha 1, T alpha 2, T alpha 3 dash dash, and you have this T alpha m, and you have this matrix of coefficient. Okay, so this is coefficient matrix here. Okay, this matrix coefficient is there. If this is the matrix of coefficients, so let's say if I write this way, A11, A12, dash dash, A1n, and then you have this A21, then you have this A22, dash dash, A2n. And probably in previous lecture, I forgot to explain this thing that I have to take a transpose of it. Okay, and that's why things were not working well with people. Okay, so let's say this is how it is. So what I'll do, this particular matrix is what? This particular matrix contains m rows and n columns. Okay, so what I'll do, I'll take a transpose of it. So I'll take a transpose of it. And transpose of this coefficient matrix, transpose of this coefficient matrix is called the matrix representation. Is called as the matrix representation of the linear transformation. Okay, so what you need to remember, let's say if you are defining a linear transformation from U to V, where U is a vector space of dimension m, V is a vector space of dimension n, then clearly let's say alpha 1, alpha 2 dash 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 alpha m form the basis in U. If I take the images T alpha 1, T alpha 2 dash dash T alpha m would be contained in V, and let's say the basis of V is defined as beta 1, beta 2 dash 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 beta n, then I can write all these elements T alpha 1, T alpha 2, T alpha n in terms of the linear combination of the basis of V. What is the basis of V? So basis of V is beta 1, beta 2, beta 3 dash dash beta n. Okay. And if I relate both of them, and if I try to write just okay, if I try to write uh, the two, I get a coefficient matrix, and I forgot to tell you in last class that you have to take the transpose of this matrix. The transpose of this matrix will give you the matrix of linear transformation. Okay, so let us do one question, and then probably you'll be able to understand all over again. Okay, so this is an important concept. Please do remember, you cannot skip this concept. Okay, so I'll do one thing. Just give me a minute. Okay, so let us do one question and then you'll be able to understand. Okay, so first let us do a simple question. People who have joined today and have were not attending the class. So, for example, if they don't know what is a linear transformation, so one question on linear transformation, and then I'll proceed further. So, those people who have not taken the class on linear transformation, see what is a linear transformation. Linear transformation is a function. Let's say I'm defining it from U to V, where U is a vector space and V is also a vector space. And I have to, let's say, I have to say that T that I'm defining a map from U to V is a linear transformation if I do this thing. And it yields me a result alpha 1 TU1 plus alpha 2 TU2. If this is the result that I get, let's say alpha 1 and alpha 2 belongs to field F, and T, if I take the image of alpha 1 U1 plus alpha 2 U2, the image I get alpha 1 TU1 plus alpha 2 TU2, then I say that this T is a linear transformation. Then I say that this T is a linear transformation. Okay, so then I say that this T is a linear transformation. So just take an example so that you'll be able to understand this concept. Let's say I define a map from two-dimensional space to a three-dimensional space. Let me define a map from two-dimensional space to a three-dimensional space. Both of them, remember, they are vector spaces in their own capacity. I have told you in the very first class that Rn over R forms a vector space. So I know that Rn, this particular thing, forms a vector space over R. Let's say I define a map of A comma B, and let's say it maps it to something like this. A minus of A plus of B, and then you have this A minus of B, and you have, let's say, B. Do you think that this is a linear transformation? Do you think that this T is a linear transformation? Okay, so in order to check that, what you need to do, as I told you, just take something like, let's say, some alpha and beta, and try to sort it out. So if it belongs to, if it's, let's say this is your mapping, and if I somehow prove that, if I somehow prove that, let's say alpha 1 and beta 1 are, or I should take not alpha 1, beta 1, I'll take A1, B1. So I'll take A1, B1, and I take A2, B2. Okay, so these are the elements from this. So let's say this is your U1, and let us say this is your U2. And let us say I want to see that alpha U1 plus beta U2 is equals to what? So it is it is equals to what? Alpha A1 plus alpha B1 plus beta A2 plus beta A2 and beta B2. Okay, this is how you, beta U2 means what? Times this, alpha U1 means times alpha times this. And if I add them up, I'll get this. So this is what I'm getting right now. T alpha U1 plus beta U2. So I'll write all these tuples in ordered form. So I'll write things in ordered form so that you don't get confused. Okay, just give me a minute. Okay, so what I'll do, I'll write things in ordered form so that you don't get confused. So what I'll do, so let's say this is, I'll write once. So this is alpha A1 comma alpha B1 plus you have this beta A2 comma beta B2. Okay, this is one. And let us say if I add them up, what I'll get T of alpha A1 plus beta A2 comma alpha B1 plus beta B2. Okay, this is what I'm going to get. And if this is the case, I've told you what my linear transformation is going to do. Okay, so alpha A1 plus beta A2, and this is alpha B1 and this is beta B2, right? And if I add them up, so if this is your A, this is your B, this is A, this is B, this is B. Okay, so what I'll do, I'll write it as alpha A1, okay, plus beta A2, and then you have this alpha B1 plus beta B2, comma, alpha A1 plus beta A2 minus alpha B1 minus beta B2, comma, and what is B? Alpha B1 plus beta B2. Okay, so this is it. And now I'm going to do one thing. I'm going to take, now if I take alpha common, what I'm going to get? I'm going to get alpha A1 plus B1. This is A1 plus B1. Then plus beta, which is A2 plus B2. And I think there would be one more thing left here. A2 plus B2 has been done, right? What is wrong with this question? Alpha A1 is there, alpha B1 is here, beta A2 is here, beta B2 is here, right? If I add them up, so this is, to somehow take out that. So alpha I have to take out. So what is wrong? Where it is going? I have this. Just kidding. Okay. So if I have this, what I'm going to get? B1 plus beta U2, right? So this is fine. This is fine. If I'm adding them up, so this is A1 plus A plus B, this is A, and this is B, and this is A, this is B, fine. This is, I think this is B itself. Okay, so B is fine. Alpha B1 plus beta B2, right? So, okay, so let me do one thing. I'll write alpha, and then I will write one thing. This is A1 plus B1, comma, there is A1, then minus B1, right from here, and then I'll take this B1 here, and then beta. This is A2 plus B2. This is A2 minus B2, and then this is B2. Okay, so I think this I can write T, and this is what? T of A1 comma B1 plus beta. This is T of A2 comma B2. Okay, so effectively what I have got this T of U1 plus beta times T of U2. So your T alpha U1 plus beta U2 comes out to be alpha Tu1 plus beta Tu2. It implies what? It implies your T is a linear transformation. Okay, now let us say I take one more example so that you'll be able to understand what is linear transformation and what is not. So I'll take one more example. So here it is. Take one example more, and that is, let's say, one of them is, let's say this. I think you'll be able to understand what I want to say. So Tx1 comma x2 is equals to what? It is equals to x1 square comma x2. This is x1 square comma x2. And if this is again a transformation from r square to r square. Now try to find whether this is a linear transformation. Just I'm giving you a minute. Try to find whether the T is a linear transformation or not. Okay. So I hope you all are watching this. I don't know. So if anybody is watching, please let me know if this is a linear transformation or not. Okay. So anybody watching that, please let me know if this is a linear transformation or not. Mm, am I audible or not audible? Okay. So let me do this. So I'll take two vectors. Let's say let x1 comma x2 and y1 comma y2 be two vectors in R square. And let us say take two elements from field also. Let's say R is the field. So I'll take two elements from field, that is A and B. Now, if I try to find this A, let's say this is your U1, let's say this is your U2. Okay, let us do this. So what it is going to yield me? It is going to yield me AX1 plus BY1 whole square, comma AX2 plus BY2. Okay, and if I want to write this up, this I'll get what? So I'll get A square x1 square plus b2 y1 b2 square y1 square not b2, it will be b square y1 square plus 2a b x1 by 1 and comma a x2 plus b by 2. Clearly, this is not equal to 8t x1 comma x2 plus b t y1 comma y2. Why? Because if I write this, what it will get? I'll get x1 ka square uh, comma ax2. So if I'm writing this, the t of x1 comma x2, what I'm going to get? I'm going to write x1 square x2. So it is ax1 plus b y1 square comma y2. So if I'm writing this, what it is going to be? It is going to be a x1 square plus y1 square, sorry, a x1 square plus b y1 square, comma, you'll have another term which is a x2 plus b by 2. So fine, this term is there, but this term is not here. So always remember, this is not a linear transformation. This is not a linear transformation. I hope it is clear. Now let's say if I take another example to explain you linear transformation, do you think this is a linear transformation? Do you think this is a linear transformation? And please do remember, this linear transformation, saying it mathematically. When I'm going to say it in physics, this is equivalent to saying linear operators. This is equivalent to saying linear operators. Okay, so so let us do it. Let us do it. Okay, so let us do. So if I'm saying that this is is that a linear transformation? So I'll do it. So again, let us take two arbitrary vectors. Let's say y1, y2, and x1, x2, and y1, y2 be any arbitrary vectors in R square. Okay. Now, if I judge this t a x1 comma x2 plus b y1 comma y2, what I'm going to get? I'm going to get t of a x1 plus b y1 comma a x2 plus b by 2, right? And if I'm going to find the like the image says what? Image says that whatever is your first one, that is in the ordered pair, whatever is your first one, you have to take a sign of it. So I'm going to take sign ax1 plus b by 1, comma ax2 plus b by 2. Okay, do you think this is equals to, is this particular thing equals to at x1 comma x2 plus b t y1 comma y2? Indeed, it is not. See, if you are going to write this, what I'm going to get, I'm going to get t, like this is what a sine x1 plus b sine y1, comma uh, a x2 plus b by 2. Again, it is not about this. This is fine, but this is not the same, because sine ax1 plus by1 would be sine ax1 cos by1 plus cos ax1 plus sine by1. So this is not equal to this. So clearly I can say that this is not equal to at x1 comma x2 plus bt y1 comma y2. So I can say that my t is not a linear transformation. Now let us come to the point I was discussing. Okay, just let me give you another question. Let's say another question. Uh, can you find this for me? Is this a linear transformation? Mm, just try to find this. Is this a linear transformation? So it has been long that we are doing linear transformation, but we'll get done with this in a couple of days. So again, the method to check this is what? You just do this thing, ax1. So I'm going to take, let's say, two vectors, x1 comma x2, and another vector, let's say y1 comma y2. They both belong to R square. Let us write T A x1 plus b y1 comma a x2. Sorry, so this a and this is, I'm multiplying it with b. So let's say a and b belongs to some R. So a x2 plus b y2. Let us see whether it works or not. So what it is going to yield me? It is going to yield me a x1 plus b y1 whole squared minus a x2 minus b y2 comma 0. This is what it is going to yield me, isn't it? Okay. Is that fine? So what it is going to yield me? It is going to yield me a square x1 square. Then you will have b square y1 square. Then you will have 2ab x1 y1 minus a x2 minus b y2 comma 0. Do you think this is equals to a t x1 comma x2 plus b t y1 comma y2? It isn't. These two things are not equal. You can confirm on your own that what it is going to yield you, it is going to yield you a x1 square minus x2 comma 0, and this will be plus b y1 square minus y2 comma 0. So clearly they cannot be equal. However, if it, so this is not a linear transformation. However, if you remove this power 2, if you remove this power 2, then obviously this would be a linear transformation. You can check it right now itself. So if I do this thing, if I do this thing, then if I say that, is that a linear transformation? Indeed, it would be. You can check it on your own. Let's say T A x1 comma x2 plus b y1 comma y2. If I have to check this, what am I going to get? I'm going to get a x1 plus b y1 minus a x2 minus b y2 comma 0. So this is how it is. And from here, if you take a common out, so what I'll do, I'll take I'll write this way. I'll write this way. A common out x1 minus x2 plus b common out. I'll take y1 minus y2, and then you have this 0. Okay. So this is equal to what? This is clearly equals to a t x1 comma x2, because if I write t x1 comma x2, what it is going to yield me? It is going to yield me x1 minus x2 comma 0. So and a. So this will give me this plus b t y1 comma y2. So clearly I can say that this t is a linear transformation. So as I told you, this is a linear transformation here. Okay. Now you see, I have already stated what are the bases. I have already stated what are the bases. So I have given you that, let's say U is defined, is a vector space of m dimension, and U is a vector space of n dimension. Let's say the basis vectors here are B1, beta 1, beta 2, beta 3, beta n. And let's say the basis set here is, what did I write there? I think alpha 1, alpha 2, dash, 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 alpha n. I told you if T is a linear transformation from U to V, so T alpha 1, T alpha 2, dash, 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 T alpha n, M would be elements in this. And if they are elements in this, then I can express them in terms of a linear combination of beta 1, beta 2, beta 3, dash, 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 beta n. So clearly, if I want to write this T alpha 1, I can write it as A, some 1, 1, and then I will write beta 1. Then I'll write A, 1, 2, and then I will write beta 2. So on and so forth. A1n, and then you have this beta n. Then if I write, so if I go on writing this, T alpha m would be equals what? It would be equals to A m1 beta 1 plus A m2 beta 2 dash dash A, and then this is mn beta n. So obviously there would be some coefficient matrix here. So this T alpha i's would be equated with some coefficient matrix, and then there would be some this matrix. This particular coefficient matrix, if I take the transpose of it, then I will obtain the matrix of linear transformation. Then I will obtain the matrix of linear transformation. So this is how we are going to write the matrix of linear transformation. Okay, is that clear? I hope it is clear till now. So let's say I'm giving you one question. Okay, so let's say I'm giving you one question, and then things will work for you. So let us define a transformation from r square to r square, a simple question. Okay, and let's say the transformation is given by tx comma y is written as 2x comma y by 2. We want to find the matrix, associated with t with respect to the ordered basis. Okay, and when I'm writing ordered basis, what is ordered basis in r square? So I'll write it here. Ordered basis in r square would be 1 comma 0 and 0 comma. So first you have to write x and then you have to write y. Now we have to write the matrix associated with this ordered basis. So how would I write? See, let me first write what would be t of 1 comma 0. So t of 1 comma 0 would be simply 2 comma 0. See, you have to take 2 into 1 and then y by 2 is 0 by 2 is simply 0. I don't think there is a problem here. And if I write t of 0 comma 1, it would be equals to what? It would be equals to 0 comma 1 by 2. It would be 0 comma 1 by 2. I hope it is clear. Now see, if this is the case and if I write this way, so t of 1 comma 0, I can write it as 2 1 comma 0 plus 0 0 comma 1. And then if I want to write t of 0 comma 1, it would be equals to 0 1 comma 0 plus 1 0 comma 1. Sorry, half, it's half, I think. So I'll write 1 by 2 0 comma 1. Okay. Now just think about this. So the coefficient matrix would be what? So coefficient matrix is 2 0 0 and half. So just take a transpose of it. Just take a transpose of it. So if I take a transpose of it, what I'm going to obtain? I'm going to obtain 2, 0, 0, half. So this is the matrix of linear transformation. This is the matrix of linear transformation. I hope it is clear. Okay, so this is the matrix of linear transformation. Now, having said all these things, now let us move to another concept that is called as the dual space. I told you there is a concept of dual space. And what was dual space? It is a space of all linear functionals. So what is a dual space? Dual space is the space of all linear functionals. And if you remember, I had defined linear functionals also. So I'll write it here so that things are easy for you. So let V be a vector space. Let V be a vector space over a field F. Over a field F. Okay. And let's say I define a linear transformation from V to F that is now on the field. Now, if I define a linear transformation from V, which is a vector space over a field F, what is field F? Field F is where your over which your vector space is defined, over which your vector space is defined. So if I define a function from V to F, then this is called as the linear functional. And I told you that this set of linear functionals form a vector space. Okay, the set of linear functional also forms a vector space itself. Okay, so let us say I have these two elements, these two vectors from V, and let's say I have some elements from field which say A and B. Then phi of A alpha plus B beta would be equals to A times phi alpha plus B phi beta. Okay, now see what is dual space. Now, if I'm saying what is dual space, so dual space is what? Dual space is the set of all, I told you, set of all linear transformations, or you can say set of all linear functionals. Now remember, what is linear functionals? Linear functionals are those mapping. Let's say I'm saying that my V is a vector space over field F. Let's say V is a vector space over field F. Okay, now if I define a map from V to F itself, so for example, one of the map I told you, which is a dot product. If you remember, I told you, if I take a dot product, then this is a linear function. So set of all linear functionals is all over, I can say, on a vector space V over the field F is also a vector space, over field F. So this set of linear functionals also form a vector space. This set of linear functionals also form a vector space. Okay, so remember this. This is called as a dual space. So this is called as a dual space. Since there's a dual space, so obviously there would be some bases here. So this is a vector space. So what is a basis? This is called as a dual basis. So if I have this dual basis, and if I want to write what is a dual basis, and let's say why I'm so much interested in this dual space and the mean space, I already told you in one of the previous lecture that in quantum mechanics, the state vectors are represented by kets. What are these kets? These are some elements of vector space, right? And corresponding to every element, like corresponding to ket, there always exists a bra vector. And this particular bra vector, we have to take a conjugate transpose and we get a bra vector. This is an element of dual space. Okay, so this is why I'm interested in this dual basis and dual space, and that is why I've been teaching you all this while. I think this is the third time I'm teaching this again, the dual space, because I find that not many people are able to follow this. So please understand that if I'm drawing a linear transformation T, then this set of all linear transformations, or you can say set of all linear transformation from the set, that is a set like vector space must be defined over some field F. So linear transformation from V to F, F is what? Towards onto the field. Okay, this particular linear transformation, that is from vector space V to the field F. What is field F? Field F is where your like whenever you define a vector space, you need a field, right? So this V is a vector space over field F. Now, if I define a map from V to F, this is called as linear functional. And set of all linear functionals in a vector space over field F is also a vector space over field F. So this dual space itself is a vector space. So now you would say that, okay, then how would you say that this is a dual, like, why do you say that this dual space is there? So for this, you need to remember something called as inner product space. That is probably topic I'll do tomorrow. What is inner product space and why it is required? So whenever you study Hilbert space, so Hilbert space is that space where your inner product space. So Hilbert space is a vector space which is equipped with inner product and also equipped with like inner product. And more specifically, we are interested in those Hilbert spaces. Let's say we are interested in this L square. What is L square? We want to know that like these are the set of all squarely integrable functions. So we're interested in this space. Why we are interested in this space? Because if your function is not squarely integrable, then you will not be able to define the probability, right? So if you remember that psi star psi d tau is equals to what? It should be 1. So from minus infinity to infinity, probability of finding a particle somewhere in the space should be 1. So for that, this particular integral should be defined. If this is not defined, then things won't work. So the function should be squarely integrable. If it is not squarely integrable, then the physical, you can say that the physicality of wave function will get like it will be wrong then. So you have to have a function which is physically realizable. So all these things are going to come a little bit later. But before that, let us first say what is dual basis. So let B be equals to what? Let B be equals to alpha 1, alpha 2, dash dash, alpha n be a basis of basis for V. Then there exist then there exists a unique linear functional. A unique linear functional f on V for each I. Okay, and this is nothing but this is Kronecker delta, such that I'll write once this phi, such that phi I alpha j is equals to 1 if I is equal to j, and it is equal to 0 if I is not equal to j. If you remember, this phi I is nothing but this is Kronecker delta. So is that clear? So what I wanted to suggest, that if B is the basis on set V, if B is the basis on set V, so we can obtain n distinct. I'm going to show it, don't worry. So we'll obtain n distinct linear functionals. We'll obtain n distinct linear functionals. Let's say these are phi 1, phi 2, phi n on V. In fact, all these linear functionals are linearly independent and they generate your dual space corresponding to V. Okay, so you can say that if they generate and they are linearly independent, then these all phi 1, phi 2, phi 3, dash, 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 phi n form the basis set. They form the basis for your V star. What is V star? V star is your dual space. So these are the basis for your dual space. So I'll talk on this at length, and I'll explain you a few of them so that you are able to understand what I'm trying to explain. I hope to meet you in the next lecture. Till then, take care.